764.
Recording in progress.
Technology.
Is equivalent to 1 atmosphere. Okay. So 1.6 times 10 to the 5th divided by 760 gives you D. So 210, which is equivalent to 2.1 times 10 to the 2. Okay. All right, so a sample of helium gas occupies 2.65 liters at 1.20 atmospheres. Now we're changing the pressure. What pressure would this sample exert in a 1.5 liter container? What equation and what's the name of the equation that we want to use here? Boyle's? Are you sure?
You have pressure and you have volume. So which law is that?
Which is Boyle's, yes. Sorry, you gotta be confident about this. He's gonna stop coming to our set. All right, so Boyle's law is P1 B1 equals P2 B2. Is the volume on if they say it? Yeah, sure. All right, and what do you say that pressure and volume are directly or inversely proportional to each other? Inverse. What is on top of it?
Wait, what?
Oh, okay. Okay, and why? Okay, so let's say we hold, if we were to solve for V2, which is, let's solve for P2, because that's what we actually want to solve for this problem. We get P2 is equal to P1 V1 over V2. So the pressure and the volume are inversely related, right? Because if the volume increases, then the pressure in the second sample is going to decrease. Vice versa, if the volume were to increase or decrease, the pressure would increase. And that kind of makes sense, right? Because if you have equal amounts of gas in a container, a smaller container is going to have more collisions with the sides of the container and more collisions with the molecules themselves, creating a greater pressure, right? Whereas if you increase the volume of a container, the molecules are going to bounce. They're not going to hit each other as frequently, and they're not going to hit the sides of the container as frequently. So therefore, the pressure would decrease in a larger container. So that's why those two variables are inversely proportional. So if we plug in what we have here, we have 2.65 liters times the initial pressure of 1.2 atmospheres over the second volume, which is 1.5 liters. And what do we get here? I got C. Do y'all get that? Let's go ahead and do number 3. I'm going to give you all a couple seconds to try to work this one. I want, in addition to solving the answer, make sure you tell me what equation and the name of the equation you would want to use here. Okay. Okay. Maybe about 20 more seconds. Before you tell me the answer, tell me what equation we're using here. Okay, so in the chat, I'm gonna go ahead and start on this problem. In the chat, Alexander said combined gas law. Jake said Charles' law. Let's see which one's correct. So let's go ahead and write the variables that we have here. Clearly for V1, we have 12.4 liters. The temperature, I'm going to convert it to Kelvin. So this would be, what is that? 300 Kelvin. 273. Wait, what is 23 plus 273? 296. So 296 Kelvin. And then pressure of 1 is equal to 0.956 atmospheres. And let's go ahead and do that for the second part, which V2 is what we're looking for. T2 would be 40 plus, that's 313. Is that right, Rich? 40. And then P1 or P2 equals 0.956 atmospheres. So clearly we have three variables. But what do we notice about one of the variables from both the left and the right side? Pressure remains constant, right? Pressure is not changing. So if we were to use the combined gas law division, they both cancel out because they're not changing. So therefore you don't need you could use the ideal gas, or not ideal gas law, the combined gas law, but you shouldn't, because you notice that pressure is not changing. Therefore you should use Charles' law. And you'll still get the same answer because the pressure will cancel out. So I would say that the best gas law to use is just Charles' law, which is V1 over T1 equals V2 over T2. 12.4 over 296 equals V2, and we're gonna multiply by T2 on both sides, so it'll be 313 here. And what do we get? What did you gotta get? No, that's okay. So when I did this, I got D. Is that what y'all got? I just use the ideal gas law to solve these types of problems without having to memorize it. So you can't use the ideal gas law. Well, let's see. You have liters, temperature, pressure. You could find the moles. It's a lot more work. It's a lot more work to do it that way than it is to just memorize these. Than it is to memorize just the individual gas law, because you would have to find the moles, and then you would have to put that into another PV equals nRT equation to find the volume in that case. So yes, it'll work. It'll just be longer. And on a test, you don't want to take a longer route if you don't have to, because time is good, right?
And to add to that, right, like you can memorize the ideal gas law and just derive all of these laws from the ideal gas law. Like you don't have to know the specific names of the laws, like Boyle, Charles, Gay-Lussac. You don't need to know any of the specific names. You just have to know like what's changing and what's constant, basically. So like when pressure and volume are changing, you use P1 V1 equals P2 V2, like stuff like that. Okay. So yeah, just derive your equations from the ideal gas law.
So the test will never ask us about people, right?
Oh,
I mean, yeah.
it'll ask you like, there's a question that says, it gives you a graph and it says on the y-axis, it's P, on the x-axis, it's T. What equation does this correlate to? And you have to know that that would be, P over T would be Gay-Lussac's law. Because, or no, if you had something like on the y-axis, it's V. On the x-axis, it's 1 over P. You'd have to know that since they're inversely proportional and it gives you a straight line, that is Boyle's law. So Yes, you should know this. Okay, so for number 4. I'll give you all a couple seconds to go ahead and start this one. Let's do 30 seconds because these are just really plug and chug type of questions, right? And this test is a lot of math, I would say.
A large portion of it's gonna be math, like this chapter and then the chapter after this one. It's gonna be
In
a
the
lot of
chapter
math.
before the solution stoichiometry, all of that.
Yeah, I'd say that's more solubility.
Yeah, that too.
These 2 chapters are the good stuff, the straight manipulation of equations.
Yeah, so we see that there is temperature and volume. So E over T. Yeah. How does one do a poll in this thing? Polls. I'm not gonna do that right now. So I'm gonna start converting my temperatures to Kelvin, so 24 degrees Celsius equals what in Kelvin? I should know that. 48. Okay. This is T1. This is T2. And then you have the B1 is equal to 1.2 liters. So we automatically know V and T, that's Charles' law, right? So V1 over T1, V2 over T2. And this is Charles's. So when we plug everything in here, we're gonna get 1.2 over 297 equals V2, which is what we're solving for, over 324. So 1.2 times 321 divided by 297. And what did y'all get?
I got C.
Okay. I got a few people saying they got C, and C is in fact correct. Okay. C, number 5. You want to do this one, Rich? Or? Gotcha. All right, Rich is gonna take over on this.
All right, so number 5. It's the temperature of an ideal gas. Ideal gas is raised from 100 to 200 degrees Celsius, while the pressure remains constant. The volume does what? So right off the bat, right, 100 to 200. What type of? How do you get from 100 to 200? What do you do, math wise?
Multiply by 2.
Right, multiply by 2. So 100 to 200, right, is times 2. So the temperature, right, basically like times 2, that's another way for being doubled. So the temperature, right, is doubled. Then the pressure remains the same, so we're going to ignore that. So they're asking about the volume, right? They're asking about volume. So what law would you use? What gas? Like Gay-Lussac's, the ideal one, Charles one, exactly. So yeah, that's the V1 T1 equals V2 over T2. And what do you know about volume and temperature in this equation? Are they directly proportional or inversely proportional?
Directly.
Directly, yeah. So when one increases, the other increases as well. That's what direct proportional means. Inversely proportional is like one increases, the other decreases. An example of this, right, would be pressure and volume. So since temperature, right, is increasing, and you want to find out what happens to your volume, your temperature is doubled. So then what's going to happen to your volume? if it's directly proportional. Right, I hear a B. Somebody says it's all, yeah, it's also doubled. So when your temperature is doubled, right, your volume also doubles. So that's why, yeah, the correct answer is B. Because of direct proportionality, things like that. Like your volume and your temperature are going to be direct proportional. Another way you could have done this, right, is write out the ideal gas law. Anybody know what the ideal gas law is?
PV equals nRT.
Exactly. PV equals nRT. So pressure, they already said, right, is constant. So you can cross that out. N is constant. And then R is constant. So you can like cross that out. A rule of thumb I always go by, right, is when they're on opposite sides of the equal sign. I notice how the volume is on the left and then the temperature is on the right. That means that they're directly proportional to each other. So when one increases, the other increases. Or when one decreases, the other decreases. But if we're on the same side, right? Like notice like pressure and volume, that would be inversely proportional. They're on the same side of equals. So when one increases, the other will decrease. So yeah, that's just another way to go about solving the problem. And the answer is B. Questions about that?
And if y'all are just trying like memorizing which one's indirect, which one's direct, just try to conceptualize it first. That'll be the easiest way to really think about this is if you have say you take a balloon, right? It has some amount of gas in it, and you take that and put it into a freezer. That balloon is gonna shrivel. It's gonna just shrivel up into the gas. It's gonna slow down the gas particles, right? So they're not gonna be hitting the sides of the balloon with as much force. Therefore, it's going to shrink the balloon. And if you were to take the same balloon and put it into a super hot car on a summer day, it's going to expand until it eventually pops. Okay, so that's kind of how you can conceptualize why this is the case, rather than just looking at an equation. If you're not so math inclined, maybe that'll help you a little bit. Okay. Let's see. Number 9. Oh, there's another one I wanted to do. I wanted to do number 6. I don't think I pasted that. Okay, number 6. Let's go to number 6. All right. A 4.37 gram sample of a certain diatomic gas occupies a volume of 3 liters at 1 atmosphere and a temperature of 45 degrees Celsius. Identify the gas. This is an interesting problem that you will see on your test. Some sort of identify the gas given these properties. Okay.
Or he might pull some other stuff and not, or he'll try to confuse you with extra wording. Basically, he'll be like, on the planet Zoloft in the city of Mordor, Bilbo goes to a shire and takes out an unknown gas, identify the gas or something like that.
Yeah. Okay. So at first, we know that PV, the ideal gas law says that PV is equal to nRT. And another thing we know is that moles, which we abbreviate N, right? N, not M, is equal to the mass of a sample divided by its molar mass, right? We all agree on that, right? That's something we learned at the very beginning, okay? It's if you want to find the moles of something, you take the grams and then divide it by its molar mass, right? So if we were to, since this is equal to N, we have an N in this equation. Let's go ahead and plug this in here. And we're going to get PV is equal to nRT over M. Molar mass, so 2 M's. All right. We all see how we kind of just derive that, right? And if you want to go further, to identify any gas, you need the density, right? So if you want to solve for density, we know density is equal to mass divided by volume. So if we solve for M over V, you get M over V is equal to pressure times the molar mass over RT, right? But this is a general equation I would say memorize. And so you can just I regurgitate that onto your test every time, because a lot of these problems, you'll be given mass and grams. And a lot of people will just want to convert that to moles and then plug it in. But you eliminate an entire step if you just memorize this equation, because it already compensates for, it has the mass and then the molar mass, and you just plug straight in and find the variable you're looking for. That works most of the time. Okay, but we're not looking for the density. We should be looking for the molar mass, right? So if I want to solve for molar mass, we just do M times RT over V times P is equal to the molar mass. That'll give us the molar mass of this compound. If we plug in everything we have, we know that it told us there's 4.37 grams in a 3-liter container with 1 atmosphere. And at a temperature of 45 degrees Celsius, which 45, when we convert that to Kelvin, it's 45 plus 273, which is 318. So I'll write that. So this is equal to 318 Kelvin. If we plug everything we have in, we get 4.37 grams. 0.0821 for the R, which is a constant, right? We know that, we memorized that. That's not something that they gave to us. Next is the temperature, which we said is 318 Kelvin. And then it was volume, which is 3 liters, and then 1 atmosphere pressure. So multiply all that out, we get, let me go ahead and bring this over here. 4.37 times 0.0821. And then times 318. I got in math of 38 grams and per mole, right? Because that's the units of molar mass. And what does that correspond to? So
Would be B divided by 2.
yeah, it's okay. So you have to look at the answer choices, Maria. Argon is not an answer choice. So let's see, what is the molar mass of argon? Is 39.948. It's close to 38, but you have to look at the answer choices, and we know each fluorine has a molar mass of 19. So F2 has a molar mass of 38, right? So this is F2 is the unknown gas. Does that make sense, Maria?
Yes, thank you.
Okay. Okay, let's go ahead and jump to number 9. You want to do this one, Rich? Yeah. Who's the calculator? Or I can.
An oxygen sample has a volume of 4.50 liters at 27 degrees Celsius, 800 torr. How many oxygen molecules does it take? So let's lay out what we have already. What quantities do we have? Yeah, anyone want to tell me? Like in the like what quantities are present?
Like
Temperature and pressure.
Yeah, we got a volume, we got a temperature, we got a pressure. And then we're trying to find what? The number of moles, right? Or first step, let's find the number of moles. So what equation would this use?
I know one.
Yeah, the idea. So, well, yeah, you went the extra mile and plugged everything in. Let's start from the beginning. PV equals nRT, Kochner, as they call it. So PV equals nRT, our ideal gas law. Our pressure, right, is 800 torr. Do we want torr or do we want atmospheres? Atmospheres, exactly. So 800 torr, we'll convert that. We know that there's 760 torr in every 1 atmosphere. So if we do 800 by 760, we will get an answer approximately
1.053.
1.053 answers. So now let's plug it back in. PVP is 1.053. Our volume is going to be 4.50 liters. This is given up there. We're trying to solve for our moles. What is our R?
0.821.
Yeah, 0.0821. And you know, like units on the R?
Atmospheres times liters divided by moles times Kelvin.
Yeah, exactly. Atmospheres times liters over moles times Kelvin. The reason why R exists is just to cancel out all your units, to make all the math work out. And then we have our temperature. So we have 273 plus 27, that should be 300 Kelvin even. All right, and as Adi mentioned before, to get our N, all we have to do is just PV over RT. So that's 1.053 times 4.5 over 300 times 0.0821. Now, if we solve that out, we will get a particular number, which is approximately
192.
0.192. And this is in moles. Moles of what though?
Oh,
Not quite O.
this is oxygen.
How many oxygen? That is crazy. Moles of O.
It's actually O2.
Yeah, just make sure if you're paying attention. Moles of O2. Because remember, right, your oxygen is diatomic. So regular O will never just straight up exist. It'll always be in
Never.
Is it?
So are we done here? Can we pack it up? We're done with the problem?
I think the answer is E, because we got 0.192 moles of O2, but that doesn't correlate to A, B, C, or D.
Yeah, I'm trying to think of what to do next. I'm kind of stumped. Do any of y'all know how to solve this problem from here?
I think it's E. Is it not E?
I mean, it might not be. You have to explore all possibilities.
Maria, help us out.
Don't solve.
I actually have no clue. Are you supposed to divide it by 2?
What's it asking for? How many oxygen
Uh,
atoms or molecules?
Oh yeah, you have to multiply by Avogadro's number, right?
Exactly. So we're trying to get Avogadro, or we're trying to get to molecules. How will we do that? Avogadro's number. So 1 mole is equal to 6.022 times 10 to the 23rd molecules. Say O2. So when we do 6.022 times 10 to the 23rd times 0.192, we will approximately get a number of
6 times 10 to the power
1.5, no, 1.156 times 10 to the 23rd. Yeah.
1.156 times 10 to the what?
23.
23. 10 to the 23 molecules. You see an answer that is on here. It's 1.16 times 10 to the 23. So yeah, our answer in this case is C, 1.16 times 10 to the 23. I feel sad for the poor souls who circled B because it's very, very close, off by 10.
Yeah, be careful, look at your exponents. That can get you on.
Molecules of O2. And somebody asked, by the way, is the test going to be this tricky?
You think, wait, what's tricky about this problem?
Oh, I didn't read it correctly. That's why it was tricky for me. I was just wondering if the test is going to be like, you know how on the last question you had to like divide it by 2 and stuff. Is the test going to be like that? Like, you know what I mean? Like that's tricky.
And the last question, number 6, we had to divide it by 2.
Or the fluorine one. The
And what was
fluorine.
tricky about this question?
It was just I didn't know you had to divide it by 2, and I was like, what the heck, argon's not even there. So, you know, and then I was like, oh, on the test it's gonna have like none of these, so I'm gonna end up circling that.
Well, actually, you don't even have to, I never divided by 2. I just noticed that everything in the answer choice is diatomic. So it's gonna be twice the molar mass. The molar mass of this gas is gonna be twice the molar mass of any of these elements, right? So like O2, if the answer was O2, then you would have expected to get
32.
32, right?
Oh, okay, that makes sense. Okay, thank you.
Okay.
Are there any other questions on this problem? Any at all? Speak now or forever hold your peace.
So wait, I have a quick question.
Yeah, what's up?
So the reason why we're going to like, so I get that we got moles of oxygen, but because it's asking for molecules of oxygen, we use Avogadro's number. If it asked for like oxygen atoms, would we also use Avogadro's number?
Yeah, exactly. You would like, because it asks for molecules here, that's why you use Avogadro's number. If it asks for atoms, right, like one molecule of O2 would have 2 atoms, right? So if it was asking for atoms, you do it that way. You just like multiply
Two
that.
atoms of O2.
2 atoms of oxygen.
Okay, so because like oxygen is always going to be presented in its a diatomic form, like you just have to kind of like keep that in mind.
Yeah,
Correct,
exactly. Like the thing to note, right, is like these chapters build on themselves. Like you learn like all your diatomic elements from the previous test chapters. Now you're like applying them in actual math equations and math problems.
Okay, yeah, that makes sense. That would have tripped me up because I would have just put like, oh.
Oh, yeah, definitely. But yeah, so it would have tripped you up if it was asking for atoms because you would have just thought it was already O. But since it's asking for molecules, I think you probably would have still got the same answer if you use Avogadro's numbers. But yeah.
Right, in this case, yeah, but I get like, since it asks for molecules and O is always presented in its O2 form, you have to like break it down further.
Yeah. So you remember your diatomic elements? Do you remember the acronym I gave y'all? Or
No, I just know that it's like in the shape of a 7.
not acronym?
The acronyms, right, is like never fear.
No, it's have no fear of ice cold beer.
Or you could use this one. Sprinkle hop.
No.
Why I use sprinkle off.
So,
Off wrinkle is better. Who are you?
Oh, yeah, no, wait. Are we in the hall wrinkle?
Diatoms.
You learned have no fear of ice cold beer at my high school.
We have no.
I mean, in my high school, we learned wrinkles.
Okay.
Point being, right, the acronym isn't important. It's just like, you know, the diatomic elements.
Yeah, just remember that. Curtis taught me. Okay, let's go and do it.
Mercury vapor containing H3 atoms, never would guess that. What is the volume of 200 grams of mercury vapor at 822 Kelvin and 0.5 atmospheres? So how'd you go about solving this problem? What equation would you use? Yeah,
Is there an easier equation you could? Maybe like a derived equation that you can just plug out everything into.
Oh, isn't it the one you just told us, which is like, where was it? It was like the molar mass times like RT over volume and pressure. Or just mass, not molar mass.
P times molar mass by R times.
Oh, that one. Okay, never mind.
copy. Paste. Yeah, is this equation right here? So we have. You able to make this bigger? All right, so this equation, right? Mass over volume equals pressure times molar mass over RT. So this is like the density of a gas. So we have our mass, right? 200 grams. And then volume is what we're trying to solve for. So 200 over V equals our pressure, right? Which is 0.5 atmospheres. The molar mass of mercury, which I do not know off the top of my head, unfortunately.
200.59. No, I just searched it out.
You might be at a table that Use all of these.
Right, so the molar mass of mercury is 200.592 grams. So 200.592 grams. Then our R, right, is the same as it was before, R is 0.0821. And then our T is 822 Kelvin. They were nice to us and gave it to us in Kelvin. So, right, we're gonna solve this out right now. So if we do a little bit of that cross multiplication, what we'll get is 200 times 0.0821 times 822 equals V over 0.5 times 200.59. If we solve this out, we'll get probably a number, hopefully.
And that number is 134.57400608.
134.507 something 8. Point is that all those digits are important. That's approximately close to one of the answers, which is 135 meters. So our answer choice would be E in that case, as a correct answer.
If you had used PV equals nRT, you would first think, okay, let me solve for the, let me
Let me solve it, the PV equals nRT very real quick. So first you'll do PV equals nRT, right? So then we'll get our 0.5, you're solving for the volume, equal the number of moles. Okay, so we have 200 grams, got to convert the grams to moles, molar mass, 200.592 grams in 1 mole. So that's some number that's close to 1.
Yeah, 200 divided by 2.5 is 0.997.
0.997, then we have R 0.0821, and our temperature 822. So then now we use our V equals nRT over P. So then if we solve this out, we will get this answer right here, 135 liters. But that's way too long and complicated, right? You have to do the extra step of like converting from grams to moles, and nobody likes that because nobody likes looking up molar masses. So look up the molar mass at the beginning, so you don't have to later. So you're on a roll.
Yes, yeah, so as a general, I like to think that if I ever see grams in these problems, I'm gonna use M over V is equal to P times the molar mass over RT, the highlighted equation. But sometimes they're nice and they give you the amount of moles. So then that's when you would directly use PV equals nRT. So it's kind of just a little bit of practice on when, like identifying when you would want to use this equation. But yeah.
So any questions about that problem at all?
There's no more problems based on the restaurant here. I think we left off. What was that number? Item 10.
Oh, that's
Choose one.
temperature pressure. Temperature will be 0 degrees Celsius, temperature should be Kelvin.
Which one would y'all like to do?
7
Give me a random number
7.
of the numbers.
Oh, right there.
Oh,
Of the numbers. of-
let's do 13.
13, okay.
No. Oh, this is average kinetic energy?
What would happen to the average kinetic energy of the molecules of a gas sample if the temperature of a sample increased from 20 degrees Celsius to 40 degrees Celsius? So what is temperature? Is there like a definition for it, or?
Isn't it like as temperature increases, your kinetic energy increases?
Why?
Because as the temperature increases, don't they like get more, I don't know, this is forever,
The
yeah,
atoms move
they
more,
move
right?
more, whatever, and they.
Y'all are complicating it too. Its temperature is proportional to the average kinetic energy. That's literally.
Oh, that's what you
Yeah,
want to say.
It's pretty much like temperature is like how you measure kinetic energy is literally temperature.
Exactly.
Their formula, like,
There's a formula. You took, I'm sure you took physics and.
besides the one happened, like using
Oh,
envy square.
Well, frankly, you don't need to know that for this class.
Yeah, that's in thermo, if you ever take thermo. You don't have to? Oh, okay. Yeah,
So,
Not take that.
I mean, if you're an engineering major.
Oh, maybe it's not engineering.
all right, so which one? Okay,
So why does that make sense, right? Why does it make sense that like as your temperature increases, your average kinetic energy increases.
Faster.
Because they're the same thing. The molecules are going to be moving twice as fast if you double the temperature.
I mean,
Twice as fast.
twice as fast. I mean, think about it this way, right?
If you're going
I
from
have-
20 to 40, isn't it doubling? That's a-
Well, we'll see, because it's not always clear from the beginning.
Because like the equation for kinetic energy is 1/2 mv squared, so if you double the kinetic energy, you're actually not doubling the velocity of the molecule since
You're
it's being-
increasing it by 4.
Yeah.
Essentially.
Oh.
Yeah, you can write all that stuff down, so you can actually see it.
I mean, think about it this way, right? Say you have 2 rods, a really cold rod and a really warm rod. Say I were to put this rod like on my arm or something, the cold one, or let's say room temperature, the room temperature one wouldn't be that bad, right? It's like this pencil, it's not doing any damage. But say, for example, I put like a scalding hot rod on my arm, what's gonna happen? I wanna move my arm away, right?
Yeah.
So that's why the molecules will move faster with more kinetic energy,
Oh.
because you wanna get yourself away from the heat. I don't know if that analogy made any sense, but that's what I use.
It's also good just to know that temperatures. Temperature is proportional to the average kinetic.
Yeah, so y'all can just remember that with temperature is proportional to the average kinetic energy.
That should go on.
So what would happen if, so the molecule of the gas sample, the temperature of the sample increased from 20 to 40? Well, let's see. What happens from 20 to 40, right? 20 to 40, you're doubling essentially the kinetic energy. You're doubling the temperature. So in that case, right? If we convert our Celsius to Kelvin, right here, we have 313 Kelvin over 293 Kelvin, which is equal to 1.07. So we'd say that our temperature is increasing by a factor of about 1.07. So it wouldn't be double, right? Because if you divide out your kinetic energies, you'll see that's it's actually increasing by like a factor of 1, not a factor of 2. So a general rule of thumb, right? If it doesn't double, but we know it increases because it's a positive number. So that's why D would be the correct answer. It would increase.
14 is a good one. You're gonna see this on it. You may,
Or may not see this on your test.
Oh, man.
you may or may not see this on your test.
All right, so 14. What conditions of pressure and temperature are most ideal for a gas? Well, first of all, right, let's switch up the question. What conditions of P and T are least ideal for a gas? When does a gas start to deviate from ideal behavior?
My top scholars.
Yeah. I mean, in general, like for any gas, there's like a general rule that occurs.
I mean, you're right, yes, but. So if it's closer to its boiling point, would you say the gas is at a high or low temperature?
Hi. Hi.
Is it high?
Yeah.
If it's right at its boiling point, so water is at 100 degrees Celsius, you say the vapor is at a high temperature?
Oh, no, low.
It's really low, because that's the borderline just to get it into vapor.
Yeah, it's pretty much the bare minimum you get.
Yeah.
So like, don't think about it when it's a liquid, think about it when it's a gas. So if it's at the boiling point, it's like absolute like lowest. So low temperatures, right, is when gases start to deviate from high, or yeah, low temperatures is when gases start to deviate from ideal behavior. What about pressure? Think about the amount of energy that's required to get water from a liquid to a gas. So keeping that in mind, would the pressure be high or low?
Yeah.
Now, see, this stuff always trips me out.
Relationship, so it'd just be like high pressure. Remember, the inverse relationship, whatever, works only for ideal gases. We're talking about when this thing isn't an ideal gas.
So water is a good example here. When you have a high pressure, you have water molecules that are. Okay. Yeah, so let me just draw up two water molecules here, and these are gonna be in the gas phase, okay? So if you have a high pressure, we can say that the molecules are interacting with each, they're constantly bouncing into each other, right? Yes, and we're supposed to read, it should be in the textbook, yes, and I know Dr. Allen talks about this in class.
Yeah, it's in probably one of his video assignments, if you look.
But yeah, so let me get back to this, so. If we have two water molecules that are in their gas phase, and they're moving relatively slow, right? What happens here is these water molecules begin to interact with each other. And when you have molecules interacting with each other, it's going to deviate away from ideal gas behavior because they're one of the postulates of ideal gas theory is that the individual particles do not really interact with each other in their container or whatever. So if you are moving slower, it's easier to grab and interact with another molecule, right? But if you're moving faster, it's a lot harder to interact with another molecule because the time that you're next to that molecule decreases, right? So it's kind of like if you're walking past someone in the hallway and you're trying to high five them, if you're walking, it's a lot easier to high five them, right? It's a lot easier to interact with them. But if you're sprinting through the hallway and they're sprinting through the hallway, you really have a very small amount of time to get your hand in the right place to interact and give them a high five, right? So that's why at higher temperatures, gases will behave more ideally, right? Give me a high five, Jake, for that one.
Wait, so it's low temperature, high pressure?
It's so for what? If at least when it's least ideal or most ideal?
These?
Correct, yeah. So for least ideal, it would be low temperature because they're moving super slow and high pressure because they're interacting with each other a lot. Now, if it's the most ideal conditions for, let's change that up. The most ideal conditions for gas would be when they're moving really fast, therefore a high temperature, and when they're interacting with each other very little, right? So low pressure, okay? So we're looking for a answer choice that has high temperature, low pressure, okay? Which is A. Does that make sense?
Yes, so real quick, in a high pressure situation, the molecules are able to interact more, is what you're saying?
Yes, because the whole idea of pressure is that you have, when you increase pressure, you're increasing the amount of interactions between the molecules. So molecules are bumping into each other more frequently. They're bumping into the sides of the container more frequently. Therefore, they're interacting with each other more frequently, right?
Right. Wouldn't
So
you
you have-
also, but isn't temperature also increasing as the pressure is high, or not necessarily?
Yes, that is true when you have a closed container, but when that's only in a closed system, okay?
Okay.
But yeah, so that's why in this scenario, you would want a low pressure and a high temperature for a gas to be most ideal.
I have a quick question. So I'm like not understanding this at all. I don't know if it's because we're gonna learn it next week or what, but so you just said that like not ideal is like high pressure because they're interacting with each other too much, but then you said most ideal is high temperature because they're interacting with each other.
So like I said, we said temperature is proportional to the average kinetic energy, right? So T is proportional to kinetic energy. And kinetic energy is proportional to velocity, right? Velocity squared. So if we have a high temperature, we have a high kinetic energy, and we have an even higher velocity, right? So like if we go back to that, trying to high five your friend in the hallway, if you're moving very slow, if you're just walking, it's going to be easy to high five them, right? Because there's more time to bring your hand up and then slap their hand and high five them, right? Like these two are doing in the classroom. But if you were sprinting like a track star down the hallway and they're sprinting towards you, the amount of time between that y'all have to interact with each other and give each other that high five really decreases, right? Because you're moving so quick, which is why at a higher temperature, there's less interactions between molecules. Whereas at a lower temperature, there's more interactions between molecules because they're moving slower. They have more time to interact with each other when they pass each other. Does that make sense?
Okay, that makes sense. Yeah, because I wrote so for an ideal gas or an ideal situation for a gas, you want them to have like less interaction with each other.
Yeah, less interaction, so less low
Okay.
pressure, and you want them to be
Okay.
moving very fast.
Okay, that makes sense. Yeah, I was like reading it and I was like, that doesn't make any. Okay, thank you. That makes sense.
Did
I
someone-
have just another quick question. With the pressure, low pressure means they don't interact a lot, but like how? You said because they don't bounce off the container or something like that?
So remember, like if you have this container here with 4 molecules inside, and then we have a bigger container with 4 molecules inside. What we know that assuming that temperature remains constant, the one that's going to have a lower pressure is going to be which one?
Wait, assuming that temperature stays constant, if you have more volume, then the pressure should be smaller.
Correct. So the one that's bigger is going to have a smaller pressure. And it's safe to
Yeah.
say that if in this bigger container, these 4 molecules can be in, they have a greater amount of space to occupy, right? So the chances of them being next to each other are smaller, right? Whereas in a smaller container with higher pressure, they're more likely to bump into each other and interact with each other. Does that make sense?
Yeah, that makes perfect sense now. So basically it's like, it's not assuming that these two things are happening at the same time. It's like, for example, if like temperature is constant, then pressure should be low for it to be ideal. And then if pressure is constant, temperature should be high for it to be ideal.
Yes. Now, it's
Okay,
not
that makes
saying,
sense.
and this question is not saying that these two are proportional to each other, right? Because we already know that.
Exactly, yeah.
Yeah, we already
Okay, that
know
makes
that.
sense.
Charles' law says that their
And-
pressure and temperature
Oh,
are.
okay, that makes, thank you so much. That makes so much.
It's sort of like a general trend at like where you'll see ideal gases and where you won't see ideal gases. Like at what temperatures and what pressures.
Exactly. Okay, let's do. Okay. Let's go ahead and let them pick one more question and then we'll go ahead. That'll be the last question for today.
All right, guys, pick one more question. Last one.
Oh, let's do 7. No, wait, no, 15.
15.
Okay, sorry, I'm sorry. I take it back. 16, okay, we're doing 16.
16, okay.
Yeah, that's what everyone agrees on.
Let's end out with a bang.
Okay, so this is nice. It gives us the moles already. And it's asking what volume of oxygen gas at STP is needed to react with 1.5 moles of C2H4.
Quick thing about STP, y'all will love these 3 letters when you get it on a test. Like if you see STP, then that means you can use a specific relationship for the, yeah, so reason why, right, I got so excited about STP is you can use a specific relationship, right, between your volume and your moles. So under STP, right, which by the way is standard temperature and pressure, that's what that means, STP. Does anybody know the conditions for it?
Like 1 atmosphere of pressure, and then temperature should be like 0 Celsius, so like 273 Kelvin.
And liters at 1 mole equals 22.4 liters.
Spoil the fun for me, but yeah, one mole, you're right,
Oh,
you're right.
oops, sorry.
You're right.
I didn't think-
Wait, how do you know that? Is that just like a given?
That's just a given. So like
Yeah.
that. There's a
That comes from this, right?
there's a question here. That actually. What is the numerical value?
What is the numerical value? What is the numerical value of the molar volume of any gas at STP?
22, right, for this question.
So number 8 is, we're just going back to number 8 to explain why you can use this relationship. So
So, right, it all goes back to this thing, ideal gas law, PV equals nRT. And then what are we trying to solve for, right, in this case, volume, right? So let's say, for example, our pressure, right? Our pressure is gonna be 1 atmosphere. Volume, we don't know what it is. Moles, we don't know what it is, and frankly, we don't care what it is. Or our moles in this case also, we do care what it is. So our R, right, is 0.0821. And then our temperature, right, will be 273 Kelvin. So when we solve this out, right, we get 1 over 0.0821 times 273. We should get an answer of approximately 22.4. That's why, right, at STP conditions, we say that 1 mole is equal to 22.4 liters, 1 mole of gas.
Wait, why did you do one? Wait, why did you do 1 over?
What do you mean?
1 over that is equal to.
For the volume, right? Because you divide both sides by all this. 1 times V is really the same thing as V.
Yeah, so.
Oh, why did I do that?
Okay,
This over 1, that over 1.
okay. Another
So flip that.
So I'm gonna actually plug the n back in because it's kind of nice to see what it does. If you solve for v over n, you get v over n is equal to this stuff right here, and when you multiply this out, you get 22.4. So if we look at the units here, it says volume per mole is equal to 22.4, right? So that's where that is derived from, okay? And it's when you have a pressure of 1 atmosphere at the standard temperature of 273 Kelvin, okay? So the volume of a gas per mole of gas is equal to 22.4. And that's why you can multiply both sides by n and you can get that relationship of the volume is equal to 22.4 times the amount of moles.
Yeah. So volume.
Question.
Yeah, what's up?
Why'd you divide divide by 1 on both sides?
So right, that's the value of the pressure. So I was just trying to show the relationship, right? So between the volume and the moles. So what I did is I divided both sides by 1 to sort of get rid of the pressure and get the volume by itself.
Oh, okay.
So ideally, your units would be in here, so you would have 1 atmosphere, and you would want to divide both sides by atmosphere, so you get the right units, but if you just didn't put the units in.
Yeah, I was being.
Oh, okay.
So
So,
going back to the previous problem, with the whole 16. So yeah, 1 atmosphere. So what volume of oxygen at STP is needed to react with that? So what we're gonna go ahead and do, right? Our oxygen, so we have 1.5 moles of C2H4, and we're trying to get to oxygen. So for every 1 mole of C2H4, how many moles of oxygen are there using our handy dandy mole ratio?
3.
3, yeah, because of our mole ratio. So 3 moles of O2. So now, right, we need a volume of oxygen at STP. Now this thing, right, the reason why it's so beautiful is you can use it as a conversion factor. So 1 mole, right, of O2 will equal 22.4 liters of O2. So that'll give you your volume. And somebody asked earlier if we can just memorize that. Yeah, you can just memorize that. 1 mole is equal to 22.4 liters at STP.
only at STP, right? You can't use this for every problem unless it says STP, okay?
If you use it under not STP, I will laugh at you.
No,
I'm kidding.
he's not gonna laugh
I'm
at you.
kidding.
I'll laugh at you, I promise.
Yeah.
All right, so when we plug this all in, right, we get a volume of 100.8 liters, which is approximately equal to 101 liters. 101 liters.
Any questions about that before I pull out the QR code? Okay, no questions.
No.
About that. That's crazy. No, oh my God, maybe this one. There it is. Please, hand yourself in.
And be a number in the machine of statistics.
Yes. But yeah, you have a question?
Yes, so what is the volume when the gas is ideal? No, it's like there's like a low pressure and a high temperature when it's ideal. How about the volume?
Is that not?
Oh,
Or does
it
it,
doesn't matter.
yeah, oh, it doesn't matter? Okay,
Yeah, because the volume could be in a small container, but as long as it's high pressure or low pressure, high temperature, which is gonna be really hard, unless you have a very small amount of gas in that small container, the volume doesn't matter. You only see temperature and pressure.
Volume.
I had one more question. So it's just going back to what Ashley Chelsea was just talking about. So I remember learning about this, and it's like when temperature is high, right? The molecules are interacting with each other more. So why is high temperature ideal for a gas if you want them to have less interactions? Wouldn't low temperature be ideal because they're moving too slow to interact with each other?
So with ideal gases, right, you actually want them to have more interactions. Because the whole idea with them is like they bounce off the container.
I don't understand.
Everything. No, hold on. An ideal gas is one that just, right, okay? So you want it to be high temperature and you don't want them to interact with each other, because when you start interacting with each other. Okay, I'm gonna go all the way back. I'm gonna stop the recording.
But high temperature, okay,
Let me
okay.
go to the textbook. I'll show you what postulates say.
Like at high temperature, average kinetic energy is like what temperature is. Like at high temperature, they're moving faster, so they're more likely to bump into each other and have those interactions.
But that's why we want low pressure too, because low pressure means less bumping into each other. Yeah, so, here, no, that's gonna go off. Where's the three postulates?
Oh, I haven't read this. That's probably why I'm confused.
There should be somewhere.
Yeah, we haven't even learned about this in class yet. Like Dr. Armand has not talked to us about this.
Oh, is that actually next week or not?
What?
You guys did you guys just start chapter 5, basically then? Yeah.
Dude, today we literally just barely talked about like Charles and Boyle's law. Like that's what we did today. Yeah, that because I'm like we have not talked about non-ideal gases at all. We haven't talked about like I don't know. See, I don't know if we're supposed to know this. I don't know what things we're supposed to know on our own and what things we're supposed to like wait for him to teach us.
I mean, if you saw on the Blackboard, right, yesterday, he did post a topics list like around yesterday night, like of all the topics that are gonna be on this upcoming exam.
Really? He did?
Yeah,
Yeah, there's like Hess's law and thermochem, and we haven't even discussed any of that. So I don't know.
Thermochem is chapter 6.
Oh, really? Oh, wait, isn't the test coming up? Test is coming up, never mind.
yeah, that's in like 2 weeks, right?
Yeah, it's 2 weeks from now.
Here it is.
Wait, like exactly 2 weeks. They have best.
Yeah, and
So,
That's
okay,
It's on best.
Yeah, it's on best bet.
okay,
Why?
okay, so as seen, okay, I'm gonna just. So here, the third postulate is the particles exert no forces on one another, right? So when we go back to what I was showing you earlier, I can just do it here.
Yeah, no.
Two water molecules. And it's good to use water as an example because it has this negative side here, which is
Yes.
right, interacting with other molecules. I think the mic can pick y'all up on the Zoom, so just give me a second here. Okay. All right, so when that third postulate says they don't exert forces on each other, right? So when you're moving fast, the amount of time to interact with each other is very slow, right? Because that oxygen wants to interact with those partially positive hydrogens, okay? And this is not something you really need to know for this class. We'll be talking more on in Gen Chem 2. But so if you move slower, what did I say? If you move slower, you're gonna have a stronger interaction between these two positive and negative ends of the water molecules, right? Because there's more time to interact with the other one. And the whole idea of ideal gases is that they don't exert forces on each other. The molecules don't exert forces on each other, therefore, they should be moving extremely quick, so that way there's not enough time for any interactions to occur between them. Okay,
What, okay, that makes sense to me, but wouldn't you say it depends on what the temperature is? Because if it's like really, really, really hot, then this makes sense. But if it's just like, like
Yeah,
room
so-
temperature.
yeah, so earlier someone said that, someone here in class, I'm not sure if you were able to hear her, but and a gas acts more ideal the farther it is away from its boiling point. So for water, its boiling point is 100 degrees Celsius. If you have gas, water vapor at 100 degrees Celsius, it's going to be in equilibrium with its liquid phase, right? Because they're interacting so much that they become a liquid instead. Okay. But if you were to increase that sample of water vapor to say 500 degrees Celsius, they're going to be moving so quick that they're not going to want to interact with, they don't even have enough time to interact with each other, that they're going to stay in that vapor phase, and they're going to be very ideal. They're going to act like a very ideal gas. All right. Does that make any sense?
Yeah, I'll just read the textbook too and I'll figure it out. Thank you though. Yeah, I like this made some sense. Thank you.
Well, ask another question if you need to. I'm sure there's going to be people that also have a similar question.
No, it's just like what I took Chem AP in high school, so it's like what I learned in that was different. So now I'm just a little lost, but it's okay. I think I just need to read the textbook, like actually read the textbook. I'll just do that.
Yeah, read the textbook. That'll help you out. I know I did read this chapter when I took the class, and it seemed to help me out understand I guess the conceptual things of this. All right. But if you still don't understand it, next time we meet or whenever, you just shoot me a email or a text message on GroupMe. I'll try to explain it again or something. Okay.
Okay, thank you.
Any other questions? What's the other question? It says a constant random motion. Combined volume is negligible. Any collisions between them. Yeah, so you really don't want them to be interacting with each other at all. Okay, I'm gonna go ahead and end the Zoom. Did everyone get the QR? Okay. I'm assuming that's a yes. Okay, that's not it. All right. You're welcome, Kristen. Have a good day. Have a good weekend too, everyone.
Thanks, you guys too.